So, hello, I'm Paul from ETH Zurich, and I'm presenting TouchInsight, a method for detecting rapid touch events from all 10 fingers on any physical surface, purely using the cameras and head-mounted devices. This project I started working on during my internship and did in close collaboration with Materiality Labs, together with Mark Richardson, Fadi Botros, Sugar Omar, Robert Wang, and Christian Holz at ETH Zurich. So this is it, TouchInsight, running just on Quest 3 in real time. It estimates the moment and location of touch events on physical surfaces solely from an egocentric perspective. It comprises a neural network to predict touch locations while accounting for uncertainties due to sensing inaccuracies. Through this, we can support bimanual rested interaction, which we believe is a key enabler for prolonged productivity work in mixed reality, including full 10-finger text input. In prior work, we actually found that users performed better, felt more comfortable, perceived high agency and reduced physical strain when interactions were aligned with a passive surface, such as a regular desk. We also explored this in a series of projects before to see how well direct touch interaction actually works in virtual reality. But as detecting input events purely visually is a considerable challenge, so far we had to use additional wearable sensors like accelerometers mounted to the wrists. Other prior work relied on external motion capture, static depth cameras, or more recently RGB cameras to support this form of interaction. In this project, our goal is to extend touch sensing to mobile head-mounted cameras. Yet, decoding such input from egocentric vision faces challenges from limited hand tracking accuracy, reduced visibility due to self-exclusion, especially of the fingertips, and quick input motions. Prior work on touch input decoding has primarily addressed user error. Due to the high precision of touch sensors, sensing error has had minimal impact and was mostly ignored for conventional touchscreens. For camera-based egocentric touch estimation, this error, however, becomes more significant due to the challenges we just mentioned before. This is why in TouchInsight, we explicitly model and consider the uncertainty about a given touch event in our input decoding pipeline. So we can leverage this uncertainty about predicted touch locations to improve the decoding of intended user input, which we demonstrate on the example of 10-finger surface text input. Our probabilistic input decoder combines the uncertainty about estimated touch locations with a user error model capturing the distribution of touch points for intended key presses, and a context-specific prior, which in the case of text entry comes from a language model. And from this, it then predicts the intended text input. So to estimate touch from egocentric vision, we developed and trained a learning-based pipeline that, based on image frames captured by monochrome cameras integrated into a VR headset, first estimates the shape and pose of the user's hands, from which we then extract key points at each finger relative to a predefined surface origin. Together with a confidence score for each hand, these key points are then input to our touch estimation network, which uses a transformer-based neural network to attend to the latest 41 frames to estimate the moment of a touch event, the finger making contact, and the 2D location of the touch on the surface. The network models locations as a bivariate Gaussian distribution to account for uncertainties due to sensing inaccuracies. We train our network using a connectionist temporal classification loss and a cross-entry loss to classify that the moment of a touch event and the corresponding finger. In addition, we use a beta-negative log likelihood loss to penalize the estimated touch location distributions. So now that we understand the touch estimation network, let's take a closer look at our probabilistic input decoder. We derive our probabilistic input decoder following a hidden Markov model where intended key hits result in touch locations, which in turn observe from tracked hand motions. We are now tasked to find the most likely character sequence based on these observed hand motions. So applying condition independence assumptions resulting from this model, reformulating the expression using probability rules, and applying assumptions about the global distribution of touch points over the surface. And now trust me, if you do the math, it should work out. We derive the following objective function which combines the sensing uncertainty, the user input model, and context priors in a single expression. So we received the estimated touch location distributions from a touch estimation network, and we combine them with a user's touch point distribution. These touch point distributions we can also model as bivariate Gaussian distributions. They characterize the touch point distributions resulting from a user's attempt to select a key via touch on a surface-anchored keyboard, and they capture the user's mental model of the keyboard and the spatial error distribution relative to the key's location. The uncertainty of the touch location due to the sensing pipeline intuitively weighs the likelihood for a given touch location according to the likelihood that a touch occurred at a specific location. And given that we integrate over the product of two bivariate Gaussian distributions, actually there exists a very nice closed-form solution for the resulting combined likelihood factor, which we can also efficiently compute using matrix multiplication. For the context prior, we use a language model, which in our case comes from a 6-gram n-gram character language model, and this then becomes like our final objective function. Right. So to validate our method, we first performed an offline experiment on a pre-recorded touch input dataset, followed by an online text entry study. We trained and evaluated our touch estimation network on a company internal dataset consisting of 385 participants transcribing short phrases and random character sequences in a Wizard of Oz setup. Participants typed on a SensorMorph touchpad while wearing a headset equipped with 4 monochrome cameras, and each participant completed 9 blocks, each lasting for 5 minutes. We then obtain egocentric hand image sequences synchronized with touch events that are also labeled with the contacting finger using additional motion capture. And we find that our method reliably detects touch events with an F1 score of 0.99 and a mean temporal offset of 3 milliseconds. It also recognizes the correct finger with an F1 score of 0.96, but note that the predicted finger label actually does not affect the downstream decoding pipeline for us. To evaluate the accuracy of our location estimates, we compare our location objective using beta negative log likelihood loss to alternative implementations for estimating the touch location. Using our beta negative log likelihood loss to estimate touch location as bivariate Gaussian distributions, so with uncertainty, we achieve a mean position error of 6.3 millimeters. Using mean squared error as an alternative loss function results in a mean position error of around 8.2 millimeters, so higher. And we also evaluated the projection of key points of the contact finger onto the surface as an estimate of the touch location. Yet, these projected fingertip and pad key points tend to be even further away from the ground truth location as recorded by the touchpad. We also evaluate our probabilistic input decoding pipeline offline. So we analyzed the performance of a text decoder under 2 decoding strategies, greedy pair character decoding and a beam search decoding on the transcribed phrases of the Mackenzie and Sokurov dataset. And these phrases were entered by participants in our held-out test set with an average entry rate of around 85 words per minute. We can show that the predicted locations of our uncertain array touch estimation network result in significantly lower character error rates compared to the deterministic and projection-based touch location estimates. And we can also show that our probabilistic decoder actually benefits from considering the location distribution instead of simply touch centroids, which overall lowers the character rate by 3%. We then also conducted an online text entry study where we invited 12 unseen participants to transcribe 3 blocks of 10 phrases from a Twitter in-vocabulary dataset, followed by 1 block of 10 phrases from a Twitter out-of-vocabulary dataset in 3 different conditions, all running live on the Quest 3. As the first baseline condition, we consider text input on mid-air keyboard, where participants enter text solely using the index finger. Here we use the default keyboard on the Quest headset with no input decoding or uncertainty estimation from our side. The second condition uses our probabilistic on-surface text entry system with greedy per-character decoding. And the third condition uses our probabilistic on-surface text entry system with per-word beam search decoding. And we find that participants actually typed significantly faster in both of our surface conditions and achieved a lower uncorrected character rate when they were supported using beam search decoding. Participants using beam search decoding achieved an average mean text entry rate of 37 words per minute and an uncorrected error rate of 2.9% on the Twitter in vocabulary phrases. Top performing participants actually achieved a text entry rate of more than 70 words per minute with an uncorrected error rate of 1.5%. So this is basically footage of our study. Participants in typing text. Participants also completed a nasal tail X survey after each condition, which showed there was a significant difference between the Surface keyboards implemented by us and Quest's default mid-air keyboard. Participants perceived that they typed faster, and they also attributed lower mental, physical, and overall task load, along with lower perceived effort to the Surface typing conditions. So to conclude, our method can reliably detect rapid touch input solely from head-mounted cameras. And what actually made this possible was our model of touch location estimates through a probability distribution that captures the inherent sensing uncertainty. This uncertainty improves the accuracy of the touch location estimates, but also it guides the probabilistic input decoder to focus not on a single point, but consider a broader surface depending on the level of uncertainty. And we showed one key application of TouchInsight, which is fast 10-finger text input in mixed reality, where we resolve uncertainties through contextual priors. But generally, we believe that TouchInsight generalizes to all on-surface input interaction in mixed reality. And I would like to invite everyone to try out TouchInsight during tonight's demo session. We prepared a fun Whack-A-Mole gaming application, and you can also try out the text entry interface if you want. And this concludes my talk. Thank you very much for the attention. I'm happy to take questions.
Shumin Jai, Google. I just have thank you for the presentation. It's really exciting. Just a couple clarification questions. One is that in your decoder, the language model looks like a character level n-gram model.
Yeah.
That's up to
six characters.
6 characters.
Yeah.
That feels pretty short. Yeah. Oh, okay. And the other question is that, so in some of your screenshots or videos, it looks like it's a type anywhere type of thing that's without the layout projected. But later, you also show the keyboard projected onto the surface. So which one?
So basically, I think it was just a different visualization. In one case, we had the keyboard. In both cases, the keyboard was anchored on a physical surface. Just in one case, it was like a VR condition. And in the other case, it was just a mixed reality condition, or like a mixed reality display output. But it was basically the same. Like in both cases, the keyboard was anchored on the surface.
So both in training and in inference,
yes,
you have the visual keyboard projected.
Okay, now I understand the question. So during training, we had a pre-recorded data set. For the pre-recorded data set, people wore like a headset, but there was no display. So they basically just had like a kind of a mounted frame of the headset onto the face with monochrome cameras, and they entered text on a touchpad, like a sensor morph touchpad, with like a printed out keyboard overlay. So they were actually not in VR, right? So they were just like looking in the physical world on this physical keyboard overlay there.
Yeah, I'll get to more details later. But the other ballpark is that if you do use a surface, then the comparison should be you have a physical keyboard on the surface.
Oh yes, we also
how does that compare?
So we also tested, compared to the physical keyboard, there the text entry words were like 68 words per minute. So we still have like a basic gap of 40% compared to our model, or TouchInsight.
So the physical keyboard is still faster?
Yes, in our cases.
Hi, I'm Taejun from KAIST. Yeah. So I think it's very very impressive and feel like a really meaningful step to, you know, remove all the burdening like wearable things to sense it. But I think I have two questions. First one is, the presentation was more about the estimating better of the touch positions, right? But I was like wondering about the instance and the moment of the touch. So were there any instance that the touch, the event of touch itself wasn't like detected to be happening, like
So,
before the estimating the location?
so actually, was a bit surprised how well it works. So we can try it tonight in
Okay.
the demo session.
Yeah.
It actually is very robust. I
Yeah.
think if you have very, very slow touches, right, maybe which are not representative of the data set, then it might fail. But I think there's like other approaches more looking into pressure estimation from a visual
Yeah.
perspective, which could probably resolve this too.
Yeah, I think I can figure out on tonight. So yeah, and the latter question was like, because it's purely vision based, I think it's pretty impressive. But I can expect so many factors that can affect, because each individual difference, like finger length is different, typing speed is different, and typing behavior different. Also, like woman, man, head size also different, which may impact the camera angles of the headset. So like, and this was a unified model, right? This is not a personalized one. So that's very, like, curious. Like how does it work? Like
So,
perfect work.
Yeah, I think you pretty much summarized why this problem is actually really, really challenging, right? I think this is like one contribution towards like a final solution. I don't think this is like it, right? So there's still like a big gap, as we just discussed. The error rate is still also like there, right? So it's not like the final solution to this problem, I think. But it's definitely going in the right direction. Yeah.
Thank you very much.
Hey, Paul. Karan from Northwestern University. Really like all your work and continuation of this work on this line. I had a quick question about the user modeling. So how did you get that? Was that an assumption that you would know the user distribution on the hands on the keyboard? And does that change with keyboard layout? Like, for example, if I resize it or shorten it, and do you need to capture that as a prior?
Yes, so the user model distribution we also get from our training data set.
Gotcha.
So there we look basically like how the distribution is on this physical keyboard, or like this overlay keyboard, right? And we aligned the size of our virtual keyboard to this keyboard so that they are matching basically.
I see. So if like it resizes, you could just like resize it back, compute it, and then.
So if you would resize the keyboard, either we would need to kind of get a new data for this specific new keyboard layout, or we would need to make assumptions, right? Maybe scale the user user distributions, but I think that's, we didn't do this. In this
quick follow-up, did you do an ablation of how much that helped? Like, for example, if you removed it, how much accuracy did it decrease?
No, actually not. Okay. Actually, I have to correct myself. There is like so we ran an experiment where we tried to see how often our touch estimate would be on the key the user would also be hitting. You know, so, and there the error rates are much higher, like 20% or so.
Gotcha. All right, super cool work. Looking forward to the demo. Thanks.
Thank you very much.